Welcome to bite-sized tutorials where we break down complex topics into quick, easy-to-digest lessons.
In the previous tutorial, we introduced distributed systems and their role in powering modern applications. Now let's dive into the CAP Theorem, a cornerstone concept that highlights the trade-offs we face when designing these systems. The CAP Theorem tells us that a distributed system can only optimize for two of three properties: consistency, availability, and partition tolerance. Let's break these down. Consistency means that every read operation returns the most recent write, no matter which node you interact with. For example, imagine you deposit money into your bank account at an ATM. Consistency ensures that if you check your balance on a mobile app a moment later, it reflects that deposit immediately. There's no confusion, every part of the system is in sync. Availability ensures that the system responds to every request, even if it does not have the most up-to-date information. In a different context, think of an online retailer during a holiday sale. If one server is slow or offline, availability means you can still browse products or add items to your cart, even if there's slight delay in reflecting stock updates. Partition tolerance is the system's ability to keep running even when communication between nodes is interrupted. For instance, imagine a network issue causes two parts of your distributed system, like a database in New York and another in London, to stop talking to each other. Partition tolerance ensures that both parts can still serve users independently until the network is restored. Here's the catch: partition tolerance is not optional. Networks are inherently unreliable, whether due to hardware failures, high latency, or external disruptions. Partitions can and do happen. A system that does not tolerate partitions would completely fail whenever nodes can't communicate, making it essentially useless in the real world. Because partition tolerance is a must, the CAP theorem leaves us with a choice between consistency and availability when a partition occurs. Let's revisit the examples to see how this trade-off works. In a banking app, consistency is critical. If you withdraw money from an ATM in one location, the system needs to ensure that no other ATM or app lets you access the same money until the transaction is fully processed. To maintain this consistency, the system might temporarily refuse certain operations, like a balance inquiry, if a network issue prevents it from syncing with other nodes. This sacrifices availability but avoids errors that could lead to serious financial problems. On the other hand, an online retailer during a big sale might prioritize availability. If one part of the system cannot immediately sync with others, it will still let customers browse and add items to their carts. Some information like inventory levels might be slightly outdated, but the user experience remains smooth and sales are not interrupted. In this case, consistency is temporarily relaxed to keep the system operational. These decisions depend on the system's goals. Banking systems prioritize accuracy and trust, while e-commerce platforms focus on user engagement and sales. Understanding these trade-offs helps engineers design systems that meet their specific needs. And while the CAP theorem makes it clear that you cannot have everything, it also shows how clever design choices can balance these priorities effectively. In the next tutorial, we will explore application, how systems duplicate data across nodes to improve performance and fault tolerance, and why this approach introduces new challenges of its own. Stay tuned.